is Philip. Um, yeah, Philip is my new friend. He's in Taiwan right now, I think. Um, he's also the blockchain engineer at Courtesy, and he's going to talk about Gödel's incompleteness theorems. So yeah, Philip, take it away.
Thanks for introducing. Let me just share my screen. Oh, can you guys see it? Can you see my mouse as well? I think I'll need to use that. Oh, awesome. Okay. So I'm going to talk a little bit about the Gödel's first incompleteness theorem. So the idea is to show the Principia Mathematica and then show how Gödel derived his incompleteness theorem from that. Please interrupt me anytime and ask questions in the middle of the presentation. No problem. Some people here must know much more about this than I do. Also, I'm not a mathematician, as I'm a software engineer, so this is an intuition. So, okay, so let's go. So it all started about 100 years ago when mathematicians began a quest to find the core principles of mathematics. So they wanted to form a formal language that could prove any statement in mathematics, right? And there was two big requirements for this new language. First of all, it had to be complete, which means that any true statement can be proved. So 1 + 1 = 2, we only know that if we can prove that. And if that's true, that is provable. And then it also has to be consistent, meaning that you cannot prove something that is false. So you cannot prove that 1 + 1 = 3, or you cannot prove A and not A at the same time. So that was the quest. So these two very brilliant guys called Russell and Whitehead, they wrote this book called Principia Mathematica, which was attempting to do exactly that. So they defined a set of axioms. We're going to talk about them later. And they started deriving everything that there was to derive in mathematics. So just so you guys have an idea, the book has almost 2,000 pages, is a bunch of volumes. And they can only prove that 1 + 1 = 2 on the second volume. So that's how precise the thing was. And then there's this funny anecdote here that Russell, one of the writers, estimated that only 6 people have ever read the whole thing. Disclaimer, I haven't, so I'm not one of those 6 people, and I don't plan to be. But on the right side here, you can see the language that it uses. But then I stumbled upon a blog post that redesigned the symbols used by Principia Mathematica to something more similar to computer science. So it helps us to analyze what's going on. So let's define some symbols. So we have 0, which means 0, and the example is 0. We have the symbol next, which means the next successor. So next of 0 is 1. You have plus. I'm just trying to define the formal language that we're going to use to show the incompleteness theorem. So you have plus. So here on the right side, you can see 0 plus next of 0. That equals 1. Here you have times. It's the same thing. 0 times the successor of 0. And you have equals. So here you can see that 0 is equal what you get when you multiply 0 for next of 0. I know it's starting to look a bit complex already, but it's going to get worse. So here's how you write 1 + 1 = 2. You can see that we start with an equal. So next of 0 is 1, next of 0 is 1, and that's inside a plus. So 1 + 1 is equal the next parameter, which is next of 0. So this statement says that 1 + 1 = 2. Okay, so more symbols. We have not. So not 0 = 1. So we know that 0 is not equal 1. We have or. So you can see here, or 0 = 1, or 0 is not equals 1. We have when and then. So when 0 or 0, 0 or 1. And you have there is such that. So there is an x such that 4 is equal to x times 2. So those are the symbols. Okay. Symbols we need. And also there's a simplification that we do here, is that when you see the number 5, we should actually be writing next of next of next of next of next of 0, because we haven't really defined all the natural numbers. We cannot do that, right? But we're just gonna use 5, and when you see 5, you pretend you saw this. Okay, so the axioms. So every formal language has to have a set of axioms that is used to derive every other statement that comes from that language, right? So the axioms are the things that you take for granted. You don't need to prove them, you just believe that they're true. When you're starting a new formal language, you want to have the least axioms possible, right? Because otherwise it gets very complicated and it's hard to maintain consistency. So they did the entire book with only 5 axioms. So the first one is when P or Q, then P. So the example is when either yam or sushi, then sushi. Then when P or, when P, then either sushi or yam. So either P or Q. So when sushi, then either sushi or yam. Then you keep going, it's all when and ors. So when either sushi or yam, then either yam or sushi. So it's just describing what it's possible to do with this language, right? These are the things that you have to believe to keep going in the book, to keep reading the book, I guess. So when either sushi, yam, or pancake, then either yam, sushi, or pancake. And when sushi is a token, then yam or sushi implies yam or token. Okay, so if this, we can actually start to derive mathematics out of this. So for instance, you can use the axiom to define the formula for AND. You can define a new symbol called AND. So AND can be defined by not, or, not B, not A. Because this is only true if B and A are true, right? Because if B, let's say B is false, not B becomes true, then or with a true inside is always true, and then the not outside would make it false. So this AND works because it only works when B and A are both true. And then you can define equal. Equal is when A implies B and when B implies A. So now you can actually start to use a bunch of different definitions and formulas. So that's what they did. They defined those axioms and they started writing these things and these definitions over hundreds and hundreds of pages. So then came a guy called Kurt Gödel. I'm not sure if it's that guy on the left or the right, but I love his name because it allows me to butcher 2 different languages at a single presentation. But yeah, he was a 25-year-old PhD in mathematics, and he started studying the Principia Mathematica. But he was a weird guy, so he decided that he didn't want to study the statements by itself. So he thought it would be easier to transform the statements into into numbers. So for each symbol in the language, he assigned a Gödel number. So remember, we have the opening and closing of parentheses. So opening parentheses is 1, closing parentheses is 3, 0 is 5, next is 7. We also have some variables. So A, B, C, it's 2, 4, 6. And he did that for every symbol that we defined previously. But well, we don't want to study only symbols, right? So we also do that for statements or formulas. So if you take the formula, for instance, there is an A where next of 0 is equal to A. So what's the Gödel number for that formula? So what we do is we take every single symbol of this formula and we get their Gödel numbers, right? So there is, if you go back here, oh, it's not written. Okay, the parenthesis is 1, right? A is 2 and so on. So you list them out and then you get a list of growing prime numbers and we power them to the Gödel number. So the first prime is 2. The first symbol in this statement is there is. So you take 2 and power that to 21. Then you multiply that by 3 to the power of 1 because the parenthesis is 1. And you do that for every symbol in that statement and you multiply them together and you get a massive unique number, which you can see down here. It's unique because it's a multiplication of prime numbers, right? So that's very cool. Then we have a Gödel number for formulas as well. And we also want to have a Gödel number for proofs. Proofs are sequences of formulas. So it's a series of statements that prove a following statement. So if you have these two formulas here and here, each of them have the Gödel number, and then we repeat the behavior that we did before. Remember, a reminder that you guys can interrupt me and ask me questions anytime. I might be going too fast. But yeah, so you have the Gödel number for this formula and the Gödel number for this formula. And you take a list of growing prime numbers. So 2 to the power of this Gödel number times 3 to the power of this Gödel number. And then you have this Gödel number down here for this proof. So this is unique and defines both of these statements. This number, by the way, is very, very massive. I think the blog post I was reading said it had 58 digits. It was actually 7 occ something, and not something meant 58 digits. I don't know how to say that word, but yeah. So what's the catch? So what he gains by transforming everything in numbers is that now he can use the Principia Mathematica language to study the numbers, the Gödel numbers that represent a Principia Mathematica proof, right? Oh, sorry, I just saw the message. Oh yeah. Okay, so what's the catch? Oh, sorry, yeah, I got a little bit lost. So yeah, so it's super interesting because it can use the own language to study numbers that represent the language, right? So, and then I can start proving things about the formulas in this language. So let's take a look at this statement here. So I'm saying that there is an A in which x of 0 is equal to A. And the Gödel number for this formula is this Gödel number here. So now if you see the sixth symbol of this formula is next, because 1, 2, 3, I'm ignoring the commas because that's not really in the language. So 1, 2, 3, 4, 5, 6. So I want to prove that the sixth symbol in this formula is a 7. How do I do that? So we know that a Gödel number for next, if you go back to the symbols, I don't know how to go back. Oh, if you go back to the symbols, next is 7. And the sixth prime is 13. So to prove that the sixth statement in this formula is a next, all you have to do is prove that the largest 13th factor of this Gödel number is 7. Because if the max 13th factor of this is 7, then in the sixth position, we have the symbol next. So how would we say that using the Principia Mathematica language, the PM language? So we can have this statement here. So let's take a look at this. What does this say? It says that there is an x in which if you take x and multiply by 5, you get 30. If x is 6, then this statement is true, right? Because 6 times 5 equals 30. And it proves that 5 is a factor of 30, right? So we can create the factor formula. So we define here the question, is it a factor? And the formula is there is an x in which x times y equals z. So to prove that the sixth symbol in this statement is the next, all we need to do is use this statement. We do an AND. I did some indentation here to help out. So we want both these statements to be true. So we ask if the largest factor, I ask if 13 to the power of 7 is a factor of the Gödel number. If it is, if this is true, then I want this also to be true. So I want 13 power to the number 8 to not be a factor of a Gödel number, right? Because if this is false, then there's a not. So false becomes true, 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 and of true and true is true. So this statement proves that the sixth symbol in this formula is a next. So it's quite interesting, right? Because we just said something about a formula by analyzing just its number. So it's about to get scary, actually. So things start to get out of control. So I'm not going to define everything here, right? Because some of these definitions are very hard to demonstrate. But Russell and Whitehead started to define a bunch of different and very useful statements. So you can ask if a number is prime. You can get the largest prime of a number. You can get the exponential of a number. You can get the next prime. And then you can use this stuff to append symbols to formulas. For instance, 3 is the symbol for the parameter. So if you multiply n by the exponential of the prime after the largest prime of n, then you're basically just adding a 3 to the end of that formula. So now we are doing statements that modify the formulas themselves, right? So it starts to get out of control. So, but since you can alter formulas, we can also ask if a formula with the Gödel number A implies the formula with the Gödel number B. So you can ask if A is the successor of B. And this is possible because it can only go from one statement to another by using one of those 5 axioms, right? So you can always see if B is a successor of A. And with that successor, we can also have this new statement that proves. So this is saying that A proves B. So the Gödel number of the formula of the Gödel number A proves the formula of the Gödel number B. And this is possible because you can just use the successor formula on every statement in A and prove that they're valid and that they imply on B eventually. Okay, so this is the final culprit that leads God to make his genius statement. So this is the substitution definition. So what I'm saying here is that I want to, on number A, substitute B for C. So how do you do that? You just replace the exponents that equal the Gödel number of that symbol with the exponents for a new symbol, right? Okay, so here is the masterpiece that God did, and that destroyed Principia Mathematica and destroyed the dreams of many mathematicians, right? So we did just define everything that we need, and now let's go to his statement. So he starts by using this statement. He proves that he's saying that there's an A that proves B. Sorry, so he's saying that A proves B. Now he's saying that there is an A where A proves B. And now he adds a not. So there is an A, there is not an A where A proves B. So this is saying that there is not a sequence with Gödel number A that proves the formula with Gödel number B. So now he just added a substitution. So he's saying that there is not an A that proves the formula that you get when you take the Gödel number B and you substitute 4, which is the Gödel number for B itself. So here is very tricky because he's substituting in the Gödel number B, he's substituting the symbol B for B itself, which is very tricky of Gödel. Okay, so let's go over it again. So this formula is saying that there isn't a sequence that proves the formula that you get when you take the Gödel number of B and you substitute 4 with the Gödel number of B itself. And 4 is the Gödel number for B. But remember that B is a variable. So you can do whatever you want with B, right? So what he did was he made B to equal the Gödel number of this statement. So there is not a that proves the Gödel number that you get when you substituting B for B. So if you put Gn instead of B in the formula, we'll get this formula under here that I'm not going to reread it because I read it a bunch of times. So now this is not a variable anymore. This is the Gödel number of this formula here. So this is the famous Gödel statement. So the Gödel statement is saying that there is no proof for the formula that results when you take a formula with Gödel number Gn and substitute the symbol B for Gn. Remember that 4 is B. Ooh, okay, but there's a catch, and yet another catch. Remember what Gn is. Gn is exactly this formula here, right? So what happens if you take this formula and substitute B for Gn? You get the formula that you just started. So in sum, so since you get the formula you just started, this is a statement that talks about itself. And what this statement is saying is that it's not provable in PM. And that is a valid PM statement. So the Gödel statement is saying that there is no proof for itself. So, but what's the problem with the phrase, I am not provable in PM? If that's a valid PM statement, which it is, because we just showed that. So if the statement is true, then PM is not complete, because there is a statement that is valid, but it cannot be proved. And it's true because we are assuming it's true, and it cannot be proved. So there are things that are true in this language which cannot be proved with the language. And if this statement is false, then PM is inconsistent, because if it is false, it's the liar's paradox, right? If the phrase I'm not provable in PM is false, then this is provable in PM. And then it breaks. So the conclusion is, if the Principia Mathematica language it is complete, then it has to be inconsistent. And if the Principia Mathematica language is consistent, then it has to be incomplete. And then, some people would just say that you can just get this sentence here and add it as an axiom to the language, right? And that's a smart cheat, but that doesn't work because you can just keep adding recursiveness. So you had to add an infinite number of statements like this. So it doesn't work, unfortunately. And then he went on to prove that that is not only true for Principia Mathematica, but that every formal language that is strong enough to define arithmetics and is also capable of it's also capable of self-reference would suffer from the same problem. So the incompleteness theorem, the first one, says that this formal language is either inconsistent or incomplete. It can neither be complete and consistent. And then there is the second incompleteness theorem, which says that no consistent axiomatic system can prove its own consistency. It can only prove the consistency of a system by analyzing it from a meta perspective. And these results, they are very sad for mathematicians, because they were hoping to be able to find a language that is able to define every true statement in mathematics. So things like the Riemann hypothesis or stuff like that, it's possible that it's impossible to prove that, even though it might be true, which is a scary proposition. And then it's also quite interesting, these results, because a lot of people use it to justify the existence of God. And there's a lot of different metaphysical arguments and ethical arguments and philosophical arguments that derive from these axioms. But it's, kind of like people using quantum physics to justify whatever they want to justify. But yeah, so I know this was too much. Here are two blog posts. Actually, it's the same blog post in English and in Mandarin. It's very interesting. They basically go through the same story that I did in a much more clear way. And they show every statement, and they rebuild things, and they show how Gödel built his statement and proved that Principia Mathematica was a dead end. And that's it. Thank you. Any questions?
Oh. Yeah, any questions? Maybe from Oscar.
Thank you so much. I have a question on the whole like prime number construction thing. Like, it's a pretty cool leap. Do you know if that was, or that's how it looked like originally? Like when he discovered this, was this like, yeah, stroke of genius where it's like, oh, you can represent it like this? Or was this initially way more complex and there was like a lot of turns and then eventually they managed to simplify to this? Or was it like this when he first came up with it?
Yeah, that's a good question. I actually don't know. But well, prime numbers are always very popular, right? And they can create unique things. And we wanted to create, well, not we, but he wanted to create unique definitions for each formula. So I guess it's possible that it was, well, it's definitely a stroke of genius, but it's definitely possible that it was his first idea.
Because it's pretty wild to like take these symbols and functions and map them to numbers. I mean, maybe it's obvious, but it seems like a wild idea to me. But yeah.
No, yeah, same actually, yeah. And also the fact that the numbers are massive, right? They don't fit, not even in a big integer. So yeah, it's a pretty cool idea, right?
Yeah, definitely.
CC, any questions for Philip?
No, but yeah, we were discussing with Oscar that OR is defined as an axiom. We also have not defined as an axiom. Then we use OR and not as axiom and define and.
Yeah, that's kind of funny. But I think this definition of and is quite beautiful actually.
So thanks very much.
Thank you.
Philip, for your sharing.